Hi everyone, I've got my favourite Year 8 class, my favourite Year 8H girls in 2020, and we're going to be going through an old probability test today as practice. So hopefully if you're watching this, you can fill it in and pause it as you go, try some of these questions. And of course, my girls in this room know that if they've got a question, they just put their hand up and we'll pause the video. All right, so first of all, you'll get multiple choice questions in your test, girls. The first question is the sample space of an 8-sided die. Now, of course, if I roll an 8-sided die, we've got a 1, a 2, a 3, all the way up to 8. So that is my sample space. Like there, you can't get a 0, can you? If you roll an 8-sided dice. So there you go. There's my sample space, 1 to 8. If I've got the probability of A is 7 out of 13, how many would be not A? 6 out of 13. Yeah, that's right. So if 7 out of 13 are A, then 6 out of 13 are not A. All right, so that should be hopefully okay. The probability of selecting a vowel from the word experimental. Well, let's write out the vowels that we want. Probability, well, E is a vowel, E is another vowel, I is a vowel, E is another vowel, and A is a vowel. So I've got a total, how many number of favourable outcomes do I have? We've got 1, 2, 3, 4, 5. Yeah, that's okay. That's fine, 5. So that's 5 out of, and how many words in, or how many letters in experimental? 12. So the probability of a vowel is equal to, we've got 5 favourable outcomes out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, so the answer is B. You're famous now. Mirabai says hi. She was a poet and I didn't even know it. Okay, now, the chance that a card drawn from a standard deck will either be a heart or a diamond. Okay, so we've been playing some cards, or we've just been, so hearts, there's 13 hearts in a deck. Okay, how many diamonds are there in a deck? 13. So we're happy with hearts, we're happy with diamonds. So that's going to be 26 out of 52, which, how would we describe that? The answer is 50-50. A heart or a diamond. So we're happy with either. Yeah? Fair coin is tossed 3 times. What is the probability of getting a head? 3 heads. Now, I think that it would be nice if we're going to be doing this, when you've got multi-stages, we probably should be thinking tree diagram. Okay, so let's draw. So although the answer is just circle and answer, you really need to show your working. So if I've got a tree diagram, I can get either a heads or a tails, and I've got a heads or a tails. So you're going to have to do a little bit of work for this one. Heads, tails, heads, tails. We've got a head and a tail. A head and a tail. Hopefully you're doing this as we go, girls. Hopefully you're not just watching. You should be doing this as you go. So when you're revising, you got to have some working to answer this. You can't just blindly just guess away. So as you can see, there's a total of 8 outcomes. There's head, there's head tail, there's so we've got head tail, head, tail, head. I'm just listing all of these outcomes. Head, tail, tail. You probably wouldn't need to do that. We can see there that there's 8 outcomes. What is the probability of getting 3 heads? Well, it's 1 out of 8. 1 out of 8. So there's my answer right there. Okay, no need to finish the tree diagram, but we could hopefully see that there's a total of 8 outcomes. That was 8 outcomes there. Okay, a 4-sided die was rolled 30 times and the results are given here. So this time when we're looking at the experimental probability, and by the way, you don't have a cheat sheet or anything in your test. So when you've got, you just need to to remember this expected number is equal to the number of trials times the probability. Okay, that is like the only formula you really need to remember going into your test skills. We don't need it for this though, because we're just being asked for the experimental probability. It's a number greater than 2. Well, 2 is not greater than 2. 3 is greater than 2. 4 is greater than 2. That is 19 things out of a total of 30. Okay. Just bearing in mind when we've got the sort of the experiment and the expected number, we're going to need to remember this formula here. Okay. All right, let's go on to and try some of these spinners. Girls, what I'm going to do is I'm going to pause this video for those in class now. I want you to try this question right now. Okay, I'm going to put and look, if you're watching this video now, I'd like you to try this question. I'm going to leave that up there. I'd like you to try it and pause it now. And I'm going to go through the answers when you unpause. Be back in a second. So you can see here that we've drawn a sample space by drawing a little table here. On the left, I've got my spinner, my outcomes, which is yellow, red, and blue. I've got a die, which is 1 to 6. You can see there that we've got a total of 18 outcomes. 3 times 6, 18. We can see what that is. And hopefully you can see that the spinning a blue, then rolling a 5, well, that's only one outcome out of 18. The probability, though, of spinning a red, then rolling a number greater than 4, well, you know, if I get my highlighter out here, you should hopefully be able to see a number greater than 4. So we're looking at, well, 5's greater than 4, and it's also red, and 6. So we're looking at 2 outcomes out of 18 for that one. What is the probability of spinning a colour other than red and rolling an even number? So let's do that. Let's do that one in blue. So we don't want a red, but we want to roll an even number. So we're looking at, that's okay, Y2, Y4, Y6. And so we need both of these things to occur. So it can't be a red and it needs to be an even number. So you can see there's a total of 6 things out of 18. So if I was to summarise, then let's write our answers and let's try and simplify when we can. The probability of rolling a number greater than 4 and spinning a red, that's going to be 2 out of 18, which of course is 2 out of dividing that by 2, that's going to be 1 over 9. And the probability of spinning colour other than red and rolling an even number is, we're looking at 6 out of 18. Let's divide both sides by 6 though. Let's simplify that please when we can. That's going to be an answer of 1/3. Okay, so hopefully girls you got that. Now I'm going to just quickly in this class, I'm going to get you to try this question please. If you're watching this video, I'd like you to pause it and have a go if you're revising. See if you can try this question. I'm going to go and reveal the answer soon. Hi! Okay, you're famous girls. All right, so look, we've got the answers revealed. First of all, we've got 5 blue balls out of a total of 19 balls, so A is 5 out of 19. If I take one of those balls away though, suddenly I've got 18 balls and this time 4 of them are blue. So the chance of taking a blue, now this is, I've circled this not replaced, which means if I take a blue out, then we've got 4 blues left out of 18. Now we really should simplify that though, shouldn't we? Because 4 and 18 are even numbers. Let's divide both by 2 to start with, and that would give us 2 over 9, and that's looking a bit better. Okay. And finally, if I was to take out another ball, I've got 17 balls, and of those, when asked for the probability of a white, well, there's still 6 white balls remaining. We haven't taken any out. Okay, so it's 6 white out of 17. All right, now I'm going to if you're watching this, you're probably revising. You're not learning for the first time. I would like you to, if you please, try this question here. We've got a little tree diagram, and we've got a 2-digit number, which is from the digits 2, 3, and 4. So you'll need to, I'll start you off, 2, 3, and 4 is the options for the first digit. Fill out the rest of this tree diagram, pause it, have a go at this question, and let's see how you go. We'll reveal that in a second. Now, so as you can see, we had to draw a tree diagram, and what we've done is we've listed the outcomes here. We've got a total of 9 outcomes, which you can see. We've got 2, 2, 2, 3, 2, 4, and so on. The sample space is listing all of those outcomes, okay? So we've done that. We've listed those together. So there's my total of 9 outcomes. But then we've been told that we've got E being the event of an even number. So even number is the event, or E is the event that we've got an even number. So there's a total of 6 outcomes there, which are for E. So therefore, the probability of an even number is 6 out of 9, which is 2/3. Likewise, though, you shouldn't have to be counting how many things are not an even number. Remember that the probability of this is really important, the probability of even and not even, they have to add to 1. Okay, so if 2/3 are even, that means that 1/3 is not even. So we should be able to make that link between those two. Even and not even have to add to 1. 2/3 plus 1/3 is 1. Let's have a look. The original experiment in A is changed slightly so that numbers cannot be used more than once. List the new sample space. Well, it would probably be fair to say that if we can't use it more than once, then the sample space is going to be changed. You can't have 2, 2 anymore, but I can have 2, 3, can't I? I can have 2, 4. If I have 3, I can have a 3, 2, but I can't have a 3, 3. And yes, I can have a 3, 4. No need to do the tree again. And if I get a 4, I can get a 4, 2. I can get a 4, 3, but I can't have a 4, 4. So there's a total of 6 things. There's my new sample space. Hence, find the probability of creating a new number which is a multiple of 4. Well, a multiple of 4 would be, that's a multiple of 4. That's a multiple of 4. 4 8s are 32. And so that would be 2 out of 6, which is also 1/3. Okay, nothing too crazy about that, but you've got to make sure that you can set up that tree diagram, list all the outcomes. If you do that, if you list all of the outcomes, then you really do. That's where most of the work is. Get that correct, and then you should be able to see that, yeah, there is 9 out in this tree, there is 9 outcomes, and I can then list those outcomes in my sample space. Create an event E, looking at it, which one's even, you can see that, oh, that's even, that's even, that's even, that's even, that's even, and that's even, and we could list that in our sample space. Okay, so hopefully nothing too crazy about this. Now this time we've got the good old Venn diagram 2-way table. Remember, this time I'm going to do this as we go. We're going to do this live, because I want to talk about when you read this and how you interpret it. A group of 30 students, okay, so let's get our highlighters out and let's highlight out 3 students. It's found that 6 students belong to the Mathletics team. So 6 students belong to Mathletics and the debating club. So it's really important. That's 6 and the debating club. 9 belong to Mathletics team only, and 7 belong to debating only. So let's draw our Venn diagram. So I'm going to call it, let's call M for Mathletics and D for debating. So let's do that. a circle, 2 circles. We've got my mathletics and my debating. All right, so let's do that. And there you go, mathletics and debating. 6 students belong to both. So hopefully you can see that that 6 will go in to there. Okay, and 9 belong to the mathletics team only. So mathletics team only means that there's not an intersection. 9 are in here. Now, we never give you all of the information. You have to work out some to yourself. 7 belong to debating only. So that means that 7 goes in here. We've been told we've got a total of 30 students. So 9 plus 6 is 15, 22. That means that 8 students neither do mathletics or debating. Okay? So you'll need to do that yourself. How many students belong to neither mathletics nor debating? Well, we've just done a Venn diagram. We can see that that's 8. Now, here's the thing. If I've got, this is mathletics and this is not mathletics. This is debating and this is not debating. A two-way table is exactly the same. Girls, are you filling this in as we go? You are? All right, now, if I've got mathletics and debating, so notice M and D, that would become a 6 there. But there are 9 people that are in mathletics that are not in debating, that would go there, 9. There are 7 people that are in debating that are not in the mathletics team. And likewise, there's 8 people that are not in mathletics or debating. Now, we could fill all those out. There's a total of 13 students in debating, which is that right circle there. That all adds to 13. This adds to 13. And there's 17 students not in debating. Likewise, there's 15 students using in mathletics, and there is 15 students not in mathletics. That is a total of 30. Okay, so this column here and this row needs to add to 30. How many students in the mathletics team? If you fill it out correctly, we should be able to fill everything out. How many in the mathletics team? Shout it out, girls. 6? No, 15. 15. Okay. What is the probability that a randomly selected student is only in the mathletics team? Yeah, so they're in the mathletics team, but it's 9. 9 are in the mathletics team. Okay, only in the mathletics team. 9 out of how many? 9 out of 30. Okay, so we've still got 30 students. 9 out of 30. Let's divide by 3 though, because we know that 3 goes into 9 and 3 goes into 30. That's going to be 3/10. And a randomly selected student is found to be in the mathletics team. What is the probability that this student is also in the debating team? This is a little bit of a different one because we've been told there's a condition that they're in the mathletics team. Okay, so it's this column here. We know that it's from there. A little bit of logic here. What is the probability that they're also in the debating team? How many of those 15 students are also in debating? 6. 6 out of 15. Okay, it's not out of 30. But why? Because we're told a randomly selected student is found to be in the mathletics team. So we're told that they are in the mathletics team. Of those in the mathletics, how many are debating is 6. Okay, so it's 6 out of 15, which if I divide by 3 and divide by 3 gives me 2/5. If you did 6 out of 15 in your calculator would also simplify as well. Should do. All right. Now we've got, I'm going to pause, give the girls a few minutes to try this question. If you're watching this at home, have a go at this because I'm going to pause now and reveal my answers shortly. Now, all right, so we had a bit of a look at this, and this last question. Girls, I've said it once, I've said it twice, I'll say it a third time. You need to be able to recognise when you're looking at this expected number, okay, this expected number, you're going to need to use this formula, okay? The expected number of something is the number of trials times the probability of that event. So in the first one, we've got what's the most common overseas holiday? Well, you can see there that they've got a total of 12 families, like take one holiday in a year. So there you go, one being the answer. Okay. Likewise, find the probability the family has chosen at random will take 2 overseas holidays. It says here we'll take 2. Well, we can see there that there is 8. I've just got that circled there. There's 8 out of 31. So we've had to total as well. Find the probability, and I've shaded this in blue. Find the probability that a new family survey will have at least 2. So that's inclusive of 2. 2, 3, and 4. So we need to add those 3 together. 8 plus 5 plus 2 is equal to 15. 15 out of 31. And right now, I'm going to do this one just quickly with you here. You've got 3,100 new families were surveyed. There's going to be some expectation on how many there are based on our little experiment, based on our experiment that we've done here. Now, how many would we expect? Expected number. The expected number is the number of trials, 3,100. Okay, so that goes in here, 3,100 times the probability of no trips. Can you see there that 4 people take no trips out of 31? So that's the probability, P, that's what we're trying to find. Okay, so we're trying to find how many we expect out of 3,100 families. So we're going to multiply that probability by how many trials we're doing, 3,100. Now, as I've said before, let's look at this. We've got really the 3,100. Let's cross multiply, simplify, like so. If I had something like this, then I could say, well, 31 goes into 3,100. Well, it's like, think about it, like I could cancel that out. It goes in 100 times, doesn't it? Okay, so that is 100 there. If I then go and multiply across, 100 times 4 is 400. So we would expect 400 out of 3,100 to be no overseas holiday each year. Now it says if 620 new families were surveyed, find the expected number of families that would take one overseas. Well, we've got to do a different one now. First of all, we've got the expected number is equal to n, my number of trials, times its probability. So the number of trials is this time at 620, but this time we're not looking at we're looking at take one overseas holiday. Okay, so we're going to work out the probability of that, which one overseas holiday is, what is that? One overseas holiday. We're looking at 12 out of 31, isn't it? 12 people out of 31 is based on our trial. So that's going to be 12 out of 31. Now let's have a look at this. So let's forget about the 0. Hopefully you could recognise that 62, 31 goes into 62 2 times. Add the 0 on the end. 31 goes into 620 20 times. So that would be 20. Let's cross it off with 1. And that would be 20 times 12. You can use a calculator for this as well, girls. 20 times 12 is 240. So we would expect, of the 620 families, we would expect, doesn't mean we're going to get that, but based on our trial run, we would expect 240 families to take one overseas holiday. Yeah? Okay. I'm going to stop that there. Thanks for watching. Hopefully that makes some sense. That's wonderful.